I'm here today to give you a little presentation about my experiences with engineering and my career thus far. I was very fortunate enough to work overseas in Formula One, which was a sport which I was always very passionate about as a child. So this is a little bit about my story and my career in engineering. So hopefully you're all familiar with names such as Lewis Hamilton, Daniel Ricciardo, Sebastian Vettel. All these people have one thing in common. They get to drive Formula One cars for a living, and they got to prove to the rest of the world that they are faster at doing it than each other. I think that these three people, as well as about 17 other drivers who are in this lucky position, have the best jobs in the world currently. So, as you just realized, Formula One cars are very loud. This is a little video that I got to take while I was visiting my favorite circuit in Europe. This place is called Spa-Francorchamps in Belgium. It wasn't very far from where I was living in Cologne in Germany. But the reason I like to show this video today is because it highlights what the cars are capable of doing, how quickly they are capable of cornering, not only cornering but accelerating and braking. These cars are so fast at accelerating, braking and cornering that they generate 4 Gs of loads on the driver. So what does 4 G of load mean? Well, if I use a little picture from myself when I was go-karting, the average human head and a helmet weighs about 5 kilos. 4 Gs of load means that the driver, when going through those corners, has to sustain 20 kilos either straight ahead or to the side. So as you can imagine, a driver's neck would have to be very, very strong. And for this reason, I always defend drivers when they believe that they are not athletes. I personally believe that they are athletes because they have to endure very difficult conditions and have to be very strong and fit in order to be able to drive a Formula One car for 2 hours. But me personally, it wasn't being a driver that I was interested in. I wanted to be an engineer. So I wanted to understand what makes these cars have such incredible performance. And this is a little picture that I took when I was working for Toyota while the car was in the pits. And it was a great picture because it highlights all the internal components in the car. So the first question I asked myself was, is it the engine? Is it this very, very powerful engine, which even though it was very small, could generate about 6 times the power of a conventional road car? Or was it the incredibly refined and hard suspension which made these cars so fast? Or was it the gearbox which can change gears quicker than what a human eye can blink? Or was it the brakes which, when the car is running at full speed, glow so hot that they look like they're on fire? Or was it maybe the tires that are only designed to last for 100 kilometers, which is about 20 times less what your conventional cars should be doing, assuming of course you're not doing a lot of burnouts in your car? Well, all these factors contributed, but the most significant and differentiating factor amongst all the Formula One cars which give them their speed is actually the aerodynamics. And that's why in this picture I like to highlight all the shapes that are contoured, all the components are contoured in a way in order to assist with guiding the air around the car. So aerodynamics are very prominent, not only in Formula One, but also for aeroplanes. Aerodynamics is what keeps aeroplanes up in the air. It helps them take off and fly high in the sky. But the wings on an aircraft are actually very, very similar to the wings on a Formula One car. A Formula One car's wings are just upside down, and instead of lifting the car up into the air, it's actually pushing the car down into the ground. And pushing them down into the ground is what gives them the grip that allows them to accelerate and brake and corner with the great ferocity that they do. So how much do they push the car into the ground? Well, at 170 kilometers an hour, a Formula One car can drive upside down. If you could drive a Formula One car in a tunnel, then it will be able to drive along the roof at 170 kilometers an hour. But that's not how fast Formula One cars can go. Formula One cars can go up to 340 kilometers per hour. And at these speeds, it's generating so much downforce, it could carry one of my old Commodores along with it. So that should give you an indication of how much downforce a Formula One car can generate and give you an idea of why they are so capable of generating the cornering and braking and accelerating loads that they do. So I really love this aspect about Formula One, and I wanted to become part of it. So from that point on, from once I realized that was the case, my goal, all my focus in the future was, how do I get involved in designing Formula One cars? And to do that, I needed to become an engineer. And that decision started as early on as high school. In high school, I decided that if I really want to achieve this goal, I need to get as much experience in designing and racing cars as possible. One of the opportunities for me to do that was actually model solar car racing in high school. And here's a picture of when I was much younger and a little bit longer hair. I was able to build and design and race this white solar car that you see on the left lane in the picture, which was, for me, a very, very enjoyable experience, and I also got to represent Australia in racing model solar cars. Once I finished from high school, I obviously decided to undertake engineering. I studied aerospace engineering because I thought that was most closely aligned with the goal that I wanted to undertake. But I also chose a university not just based on the degree that it could offer me, but also the extracurricular engineering projects that it had available. And the university that I particularly went to had the solar car project called SunSwift. SunSwift was a real-life solar car that races from Darwin to Adelaide. And I went to that university, had the opportunity to design and build and race that solar car. So I had the opportunity to do things like composite design, which is what you see on the left, or composite manufacture. We were actually sponsored by a company called Boeing, which allowed us to use their clean rooms where they'll manufacture aircraft components for us to actually manufacture components for our car. But this project also introduced me to engineering research, the opportunity to be able to solve problems by using our engineering knowledge. And with that opportunity came the opportunity to manufacture solar cell modules, which were for the first time curved and bent to follow the shape of the car. So my passion for aerodynamics, which was why we needed to bend and curve the solar modules to fit the shape of the car, actually led me into designing solar modules as well. And over the last 2 years of my involvement during my undergraduate degree, I became the project leader of the team. And that gave me experience with dealing with the media and with the public, and as well with stakeholders, people who sponsor the team and want to fund and support the project. So despite having that experience, which I thought was quite unique, once I finished my undergraduate degree, I still wasn't successful in finding a job in Formula One. So then I had to decide, what could I do next? I needed to do something that I thought would further increase my value to Formula One teams. I decided to do a PhD so that I could learn more about aerodynamics, more about computational fluid dynamics and wind tunnel testing. Computational fluid dynamics and wind tunnel testing are tools which are readily used by aerodynamicists, so I thought it was important for me to know as much as I could about that. And to achieve that, I undertook a PhD. So what would I study? Because a PhD requires you to solve a problem, understand a problem that hasn't been considered before. I found a problem which was relevant to Formula One cars. I investigated how the performance of a downforce producing wing varies in the presence of a wheel, and I used CFD as well as wind tunnels to investigate this problem. Unfortunately, my university at the time didn't have a wind tunnel that would allow me to investigate the problem as I required. So I actually decided to build and design one. And here's a picture of the wind tunnel schematics that I created and the final product. And we also used lasers to be able to take measurements of the airflow behind the wing and the wheel so that we can understand how the flow structures vary around the wing and the wheel. And some of the results that you see here summarize how these flow structures varied. I was for the first person that was able to understand why previous people who studied the same problem were getting different results depending on what the geometry was that they were testing. And I found that the span, the amount of overlap that the wing had across the wheel, was a significant factor for why all my predecessors were finding different results or conflicting results. During the same time, I also took the opportunity to work with some local motor racing teams, and this is a Formula 4000 team that I used to work with, so very similar cars to Formula 1. And I offered my services for free just so I could get some experience with them and to understand how I can better improve myself to prepare myself for Formula 1. And one of the things I did for these teams was actually design some barge boards, so some of these components here, and looked at how this can improve the performance of the cars, and finished up building them and mounting them onto the car and testing them on the track. So the other fantastic thing about working with the local motor racing industry was it started to generate contacts for me that could introduce me to people in Formula 1, and that was a very valuable thing. I then used those contacts to try and convince the Formula 1 teams overseas that they should collaborate with me, that they should support my research. But unfortunately this was unsuccessful because Formula 1 teams are very, very secretive. They hold their intellectual property with great value, and so that wasn't something that they were willing to share with me. Instead, they invited me to visit them the next time I was in Europe and whenever I had a European passport. So once I had that invitation, I didn't wait till the next time I was in Europe. I actually made plans to go to Europe. And in 2004, after I obtained a Greek passport, thanks very much to my Greek heritage, my parents being from Greece, I arranged to make trips to go to Europe, and I visited many motorsport teams, and that is included the Honda and Toyota Formula 1 teams. I then returned home and continued working on my PhD, and even at this point I felt that my dream will never happen, but I kept my contacts overseas up to date. I kept them up to date with my progress, and I kept being in touch with them so that they knew what I was up to and what stage I was at. By mid-2006, I had a very pleasant surprise. I eventually received an email from Toyota Formula 1 asking me if I would be interested in a Junior CFD role. And I think you can guess that later that year there was no hesitation. I was in Cologne ready to start my dream job. And this is a picture of me just before New Year's, about 2 days before I started a job, with probably who was my most instrumental contact, Jean-Paul Ballard. And we were standing on one of the bridges in Cologne, enjoying New Year's Eve and trying to avoid all the fireworks which were being fired all around the place. So while being a CFD engineer at Toyota, I got to do a lot of interesting projects. One of the things that really highlighted to me was how my PhD was able to directly contribute to my progress at work. One of the first jobs that I had to do was understand why the drivers were complaining that when they steered the wheel, the car's handling would change. And I later found out that this was an interaction between the front wing and wheel, so exactly what I'd studied in my PhD. And I was able to assist the team in designing a wing which will make the car a lot less sensitive to steering the wheels. And then in 2009, the Formula 1 regulations changed, and we had to design a brand new wing, which this time spanned across the entire front of the wheel. So again, something very closely related to my PhD. And that opportunity allowed me to introduce a concept which was new to Formula 1 at that time, slotted front wing end plates. And that's a concept that is still being used today. The only thing that's changed is the number of slots that are being used in the front wing end plates. So that's very exciting that I've made that little contribution to this sport. Unfortunately, in 2009, at the end, the global financial crisis hit, and the impact on me personally was that Toyota decided to withdraw from Formula 1. And I fortunately very quickly found a job at the Williams Formula 1 team as a senior CFD engineer. And at that point, I helped them understand how to make the front wing interact with the rest of the car better, and how to introduce a component, which is this under-nose turning vane, which I'm pointing with the yellow arrow, which if you adjusted its shape would allow you to tune the front wing into the rest of the car and make the whole car work better as a whole. And that helped the team make more significant gains every time they made changes to the front wing. And shortly after that, I was scouted to join the Caterham Formula 1 team, which at the time was Lotus, as their head of CFD development. And that meant that I was responsible for all the staff that were under using CFD as a development tool. I also was given the role of being the Wind Tunnel Special Projects Group leader, and that meant that we got to investigate all the problems which were a little bit more complex than just refining the aerodynamics of the car. These included things such as the blown exhaust, which not only had an impact on the aerodynamics, but the performance of the engine. So we had to liaise with the engine department from Renault, and also the full-scale department, which had to implement the exhaust system and make sure that it wasn't going to burn the car where we wanted to route it. So it was a very eye-opening and entertaining role. So at all of these three teams that I worked at, there was a various number of people being used to design and build and race two cars. At Toyota, it was approximately 1,000 people being used to design these cars and build them and race them. At Williams, it was about 450, and at Caterham, which was the smallest team I worked at, it was probably no more than 350. But why are so many engineers required to be able to do this? And what could we possibly do all day? There's two cars that are racing around the tracks. How much work is there possibly to do? Well, the reason there's so much work to do in designing a Formula One car is because every single component is unique to a Formula One car, and it suits its special requirements. As a result, every single component is analyzed, refined to achieve the highest performance possible in the given amount of time that we have to do that. And every component is frequently redesigned and regularly progressively improved to enhance the performance of the car and to help the car go faster at a subsequent round. This happens non-stop every day of the year, regardless of when the races are held. And as a result, the car that starts the season is very, very unlike the car that finishes the season. They almost have no resemblance to each other at all. In order to achieve this constant progress, especially for the aerodynamics department, which is where a lot of the progress was focused on, there is a large array of resources which were available to us. These included CFD simulation software, which was like some of the pictures that I showed you before. To solve CFD simulations, you need very powerful, very fast computers, and as a result, Formula One teams have among the world's largest computing clusters. I think NASA was probably the only institution that had larger clusters than what Formula One teams do. Wind tunnels are required, like the one that I built, but these ones were so big that you could fit a whole car in, and when we wanted to do wind tunnel testing, we could actually walk into the wind tunnel and look at the model car that was there. We have a large array of 3-axis and 5-axis CNC mills to manufacture components out of metal, as well as large-scale 3D printers, which usually made components out of ceramic, but were also capable of making things out of titanium. So as you could see, we're very, very well resourced to do our job. As a result, a large investment was required to fund the Formula One team, and the staff were held accountable by the stakeholders and the sponsors in order for the performance expectations to be met. And for the aerodynamics team, that meant having progress charts like this one. The red line represents the expectations of the sponsors and the team owners. At the beginning of a season, the head of aerodynamics would sit down and discuss with the sponsors and the team owners, this is what we expect our results to be, and they will negotiate what resources were required to achieve those results, and this line will get drawn. The progress of the aerodynamics department was then tracked as this green line that you can see, in this case above the red line. When the green line was above the red line, when the results were exceeding the expectations, the sponsors and the team owners were happy. When they dipped below, the sponsors and the team owners are very unhappy. And the problem when sponsors and team owners are very unhappy is they want to make changes, and that usually results in staff being fired, which unfortunately I've lost many friends working in Formula One teams because of this sort of situation. So as you can see, working in Formula One was very exciting, but it did have some of its negatives. Some of the personal challenges that I encountered was my family is based in Sydney, and as a result, having my dream career took me far from my family and friends. It also means that you can't establish yourself in one location. In the space of 4 years, I lived in Cologne, then I went to Oxford, then I went to Wantage in England, then I went back to Oxford again. So as you can see, even if you are based in the factory or the design team and you're not traveling with the race team, there is still some sort of travel associated with working for these teams. And also, this is probably one because of my own lack of discipline. When you love your job so much, it's actually quite difficult to find an appropriate work-life balance because you're so excited by your job. That's the only thing that you can really think of. And there's also professional challenges. 2 of the 3 teams that I worked for previously don't even exist anymore for financial reasons. So job security is definitely one of the issues associated with this role. Especially with the smaller teams, it's often unsure if they're going to be around soon after. Another professional challenge was the motivation for research was not always governed by what was the engineer's perception of what was necessary, but sometimes of what the stakeholders and the team owners thought was necessary. And the stakeholders and team owners, not being engineers, will probably feel that what the winning team has is what is best to have, and that is what they will guide your research to be. And finally, research was focused on solving problems and not understanding them. If you could make the car faster, it didn't matter if you understood why you made it faster. The only thing that mattered was that you did. And so these were the 3 challenging things professionally for being involved in this team. So why did I decide to leave Formula One to join academia? So while it was very fun and exciting, the resources being used in F1 were not really translating to making the vehicles that we use every day any more efficient or any more affordable or even faster. There's probably only one team that can claim that they are making their cars faster because of their research in Formula One, and that's Ferrari. All the other teams cannot really make that claim. And this was not always the case. When I was growing up in the mid-80s and early 90s, Formula One cars were instead high-speed experimental vehicles which were pushing the boundaries of technology and innovation. During this period, there was developments such as ABS, traction control, and active ride height control. All these things now you will find in most modern cars, and they were first developed in Formula One. Formula One is not the laboratory that it used to be. Unfortunately, Formula One now is a very effective and wide-reaching marketing tool, which means that the regulations have changed so that costs can be minimized and research is actually reduced. And for this reason, I decided to return to academia because I wanted to use the knowledge and skills that I'd gained in my lead up to Formula One to undertake research that will provide a greater and more significant assistance to humanity in general. So soon after returning from overseas, I undertook my first role in Australia was to undertake a consultancy role helping my old solar car team, Sunswift, with their new design of a solar electric sports car. And this was exactly the sort of thing that I wanted to do returning back to Australia. Sunswift Eve was the car that they produced. Is a picture of me on the day that I got to drive. This is actually the first car I ever got to drive that I worked on, which was very exciting for me. But Sunswift Eve went on and broke the FIA world record for the fastest 500 kilometers ever completed by an electric vehicle. And they did this with an average speed of 107 kilometers an hour. And the really exciting thing for me about this achievement was it's breaking the perception that solar cars or electric cars are slow or they have lack of range. This is definitely not the case. This car's completed 500 kilometers on a single charge at 107 kilometers per hour, which is probably more distance than what anybody will travel in a week. And then one of the things that attracted me to Macquarie University is the research being undertaken by Professor Itsu Sen and his group in ASAM. And they are using CFD simulations to assess the likelihood of brain aneurysms bursting. So a brain aneurysm, if it bursts, is fatal for a patient. CFD is the exact same software that I was using to design wings for the car or for a plane. And this exact same software is now being used in a biomedical application. So that was very exciting for me that you can translate that knowledge into a completely different field. So once joining Macquarie University, we established our own wind tunnel research laboratory, and this is a picture of our wind tunnel with a PIV machine, which lets us take measurements in the air behind objects. And our motivation for doing wind tunnel testing at Macquarie University is so that we can understand the aerodynamics related to vehicles to reduce the environmental and economic impact that they have. One of the investigations that we're currently undertaking is understanding how does the aerodynamics of a vehicle traveling through a corner work. And this isn't only relevant to racing cars or conventional cars, but it's also relevant to submarines. Any object which travels on a tight radius relative to its length is something that experiences a different flow at the front and the rear. And unfortunately at the moment there's no experimental technique to test for such a condition, and this is one of the problems that we're trying to solve currently with our research. All vehicles, or most vehicles and cars, have wheels, and the aerodynamics of a wheel is a huge impact on the drag and the fuel consumption that a car has. And for this reason, we're investigating the aerodynamics specifically of wheels and trying to understand how we can reduce the drag of wheels to better improve the fuel efficiency of cars. One other aspect which is very large at the moment in the automotive industry is self-driving cars, and at Macquarie University we're looking at the possibility of making a self-driving wind tunnel model, a car which can drive itself in a wind tunnel, so that we can reduce some of the consequences or some of the reasons for having poor correlation between wind tunnel and the road. And so this car here is designed so that it can drive itself on a conveyor belt inside the wind tunnel and measure the forces that it experiences when it drives against the air. Another reason for introducing self-driving cars is in the future it's anticipated that on highways self-driving cars will be able to drive very closely to each other, and by doing so they'll be able to reduce their drag further and improve fuel consumption. So unfortunately at this stage it's not really understood how much more a car can reduce or improve its fuel consumption by following another car closely, and that is something that we are investigating here at Macquarie University as well. How does the drag of a car behind or in front of another change when they are traveling in close formation? There is also discussion about aircraft using the same technique to reduce their fuel consumption, but aircraft generate vortices, which are like little tornadoes off their wingtips, which can adversely affect the performance or the lift characteristics of an aircraft behind it. And so one of the investigations that my PhD students are currently undertaking is how can vortex decay be predicted, or how can we understand what a vortex decay will be and how can we control it, because these vortices can affect aircraft which are further down from the existing aircraft. And of course, part of being an academic is teaching, and I don't see it as teaching, I see it as preparing students for achieving their future goals. How do I prepare students for their careers in the fast lane? So one important way of doing that, in my opinion, is to provide students with as much practical experience as possible. And these are some pictures that we've taken of our engineering students in an engineering workshop, learning how to use lathes, learning how to use mills, learning how to use hand tools to manufacture something out of metal. And this means that they get to get their hands dirty, which I think is very exciting and a lot of fun. And then it's also the type of projects and assignments that we set. So I teach design, and one of the assignments we had to do for design was design a device that could eject a golf ball after traveling a particular distance along a course over a particular wall. And this is one particular student's way of solving that problem. And then I think for the most exciting project that we have going on at the moment at Macquarie University, it's the MQ Speed project. The MQ Speed project is an extracurricular engineering project which will hopefully allow students to apply their engineering knowledge in a dynamic and exciting project. So the MQ Speed team are going to design and build a human-powered vehicle which can break the world land speed record for such a vehicle. And currently, this stands at 134 kilometers per hour. So what is a human-powered vehicle? Well, a human-powered vehicle is a vehicle which has a person pedaling inside, and it's the person pedaling or the athlete pedaling inside which powers the vehicle. So the speed that the vehicle can obtain is a combination of the ability of the athlete to pedal as well as the efficiency of the vehicle. And it's these two items in combination which help achieve these world record speeds. Thus far, the students have designed a simulator to help improve the understanding of an athlete's ability to generate the power that's required, and for also to help the students understand when they make changes to the vehicle design, how that's going to affect the final outcome of the speed that the rider will achieve. There have also been CFD simulations undertaken which are investigating the aerodynamic shape of the vehicle. And as you can see from the left where the team started, they designed a vehicle that they estimated could achieve 118 kilometers an hour. But after some aerodynamic refinement, they believe they now have a vehicle that can achieve approximately 140 kilometers per hour. If that is correct, then that is great news, because that is a large step above the world record. So I'm sure there's some things that haven't been considered there just yet. There's also been some design for internal composite structures, which is what you see here, the internal frame, which is made out of composites for a number of reasons. First of all, so that it easily follows the shape of the vehicle that's being designed. Also, to keep it light and stiff. And finally, and most importantly, to keep the athlete, the occupant, safe in the unlikely event of an accident or a crash. In order to manufacture composites, the team needs to have a CNC mill which they can make the molds that they require. Unfortunately, the team doesn't have the funds to purchase a CNC mill of the scale that they need, and for this reason they undertook the activity of designing and building a CNC router, which is what you can see here, which they're nearly close to completing. So, in conclusion, I'd like to say that for those that are passionate, enthusiastic, and driven to become engineers, there are lots of exciting projects that exist all around the world. I don't expect students to all be interested in Formula One, but I hope that they all have their own enthusiasm, their own passion, and their own reason for wanting to become an engineer. But the first step is to understand what that is. What excites you, what motivates you, and what's going to drive you to study, to work every day. If you love your job, it's not going to feel like work, it's going to feel like fun. So once you've established what that is, make a plan that will help you achieve your ambition. This should include what education required to do that, but also how to get as much experience as possible along the way to prepare yourself for an opportunity when it presents itself. And finally, do not underestimate the value of contacts. Exciting engineering careers are usually very competitive, and for this reason you have to find the right people to demonstrate your ability to. Once you've demonstrated your ability to the appropriate people, they will generate opportunities for you. All you have to do is be ready when those opportunities arise. So thank you very much. I hope you've enjoyed my story, and I'll be happy to take some questions from you. I think both equally play a role, but I believe that the development of aerodynamics for road cars is something that hasn't really been considered as much as what engine design has. So you'll see there are many cars which are hybrids currently on the road. A lot of manufacturers such as Toyota are putting hybrid drivetrains to improve the fuel efficiency of the engine in vehicles, but they're not really changing the body. You can buy a Camry or a Corolla, which is a hybrid or an internal combustion engine. This doesn't change how much power the vehicle requires to drive. So I believe currently the emphasis is on engines, but that has to change in the future to also include aerodynamics. involved a lot of sleepless nights. That's one thing for sure. But it introduced me to a lot of the aerodynamics concepts and structures concepts that you need for designing items such as vehicles such as aircraft or Formula One cars. The structures and the aerodynamics are specific to that which are unique. If you are not studying mechanical engineering, for example, is probably a lot of more focus on composite design, a lot more focus on fluid mechanics, a lot more focus on control systems. So how do we keep an aircraft stable in the air? How do we keep it light in the air? That's why we're studying composites. And how do we generate the lift, which is why we're studying aerodynamics. So I think that's some of the unique features of an aerospace engineering degree. Now, I think the thing that I would add to that is that aerospace engineering degrees are very exciting, very interesting. The opportunities for aerospace engineers in Australia, though, is very limited. If that's a degree that you plan on undertaking, then it is something that you would have to be prepared to travel overseas in order to forge a career in that path. Whereas mechanical engineering is probably a lot more open and possible locally as well. I think that's yes and no. I would say yes because I chose the university that I went to specifically for the opportunities that it gave me, such as the solar car project. So I feel that solar car project is what gave me an edge eventually over a lot of my fellow graduates from the engineering degrees. And then I would say no because it doesn't matter where you study, as long as you look for opportunities to differentiate yourself as a student, I think then you will have the opportunities come to you. And for me, the solar car project was what differentiated me to begin with. I would say the answer is yes, because nature has evolved to effectively give the best result that is possible for that particular animal. And it's not just birds that aerodynamicists look at for inspiration. It's also fish or whales or sharks or seals. A lot of these animals are being studied by my colleagues to understand how they can make vehicles perform better. One other example is fish scales. Fish scales are believed to be able to reduce the drag of a body because of their shape, and that's something that's frequently being investigated by aerodynamicists. On top of that, you have the wingtips on birds, such as an eagle, which I believe looks very, very similar to what you would see on the Dreamliner. So that's about controlling the vortices that you get on the tip of a wing. So yes, definitely nature is inspiration for us as aerodynamicists, and I think aerodynamic shapes should always look very smooth, very organic, and almost like something that belongs in nature. My personal opinion is the opportunity to get practical experience. I think every university is going to teach you the theory. They're going to teach you the knowledge that you need to know. But the thing that differentiates engineers from scientists or from a lot of other people that can study physics and chemistry and maths is understanding how to apply it. And for this reason, I believe that practical experience is important. You've got to be exposed to problems and practice applying the physics and the maths and the chemistry and all the other sciences that you learn as part of an engineering degree to solving a particular problem. I think the answer to that is a VW X1. And maybe someone can Google that if they got a phone in front of them. But I believe the VW X1 is probably the most extreme example of how a efficient aerodynamics of a conventional car can be. Yeah, I don't know what the aerodynamic values are, but I believe that's the answer to the question. I don't even know if it's in production yet. It might even be just a concept car at the moment. I think it's the opportunity to do the research. It's being able to solve problems that are going to make a difference. So I think that's the most enjoyable thing at the moment. And then the other thing I would add to that is seeing the development of the students, seeing some of my PhD students now go on and achieve their goals, their ambitions. So that's quite satisfying. When I was involved in F1 cars, they used to have 2.4 litre V8 normally aspirated engines, and they could generate about 800 horsepower. Now, in the last 2 years, that's changed. They now have hybrid engines, hybrid turbo engines, and they have the combination of a V6 engine and turbos and electric motor generators and electric motors, which all generate about the same amount of power as what the V8's used to, but with 1/3 the fuel consumption of what they're used to. So while a lot of people don't think they're good engines because they're quiet and they're not very exciting to watch at a track, they actually have made quite a big step forward with the current engine regulations. Thank you very much for having me, and yeah, I look forward to hearing one day hopefully of what your careers are going to entail and how excited you are about them.